boron family, carbon family, nitrogen, oxygen, halogen, and noble gases. And the whole periodic table is divided into 4 blocks. S block contain alkali metals, alkaline earth metals. D block contain transition metals, and F block contain inner transition metal, which is further divided into 2 groups, lanthanide and actinide. Main group element. The main group element is divided into alkali metals group 1, alkaline earth metals group 2, boron family group 13, carbon family group 14, nitrogen 15, oxygen 16, halogen 17, noble gases 18. Hope you know that all groups vertical column found in the periodic table are called families, and all elements in each group or family share many physical and chemical properties. Boron family. The boron family include boron, aluminium, gallium, indium, and thallium. Boron is a fairly rare element. The abundance of boron in earth crust is less than 0.001% by mass. Aluminium is the most abundant metal and third most abundant element in earth crust, which is 8.3% by mass, after oxygen, which is 45.5%, and silicon 27.7%. General properties. As you know that they have a ns2np1 electronic configuration. Boron has 2s2 2p1, aluminium has 3s2 3p1, gallium has 3d10 4s2 4p1, indium 4d10 5s2 5p1, thallium 4f14 5d10 6s2 6p1. The electronic structure of these elements are more complex than for the first two group of elements. Atomic and ionic size. As we know, on moving down the group for each successive member, one extra shell of electron is added, and therefore atomic radius is expected to increase. However, there is a deviation. Atomic radius of gallium is less than that of aluminium due to the presence of poor screening effect, or we can say additional 10d electrons. As you know that the atomic radius of gallium, which is 135 picometer, is less than that of aluminium, which is 143 picometer. Ionization enthalpy. The ionization enthalpy values expected from the general state do not decrease smoothly, but decreases from right now boron to aluminium with increase in size. This and then increase from indium to thallium due to the inability of D and F electron, which are showing low screening effect, as you know, to compensate in the nuclear charge. General properties. Electronegativity. As you know that down the group, electronegativity first decreases, that is from boron to aluminum, which is you can see that in the table. Boron has 2 point electronegativity 2.0, aluminum has 1.5, which is decreases. After that it is increases from gallium to thallium. Gallium has 1.6, indium has 1.7, and thallium is 1.8 because of the discrepancies in atomic size of the element. Physical properties. As you know that boron is a non-metallic in nature. It is extremely hard, black colored solid. It exists in many allotropic form. Boron has unusually high melting point. Rest of the member are soft metal with low melting point and high electrical conductivity. Gallium with unusually low melting point, which is at 0303 Kelvin, could exist in liquid state during summer. Its high melting point is 2676 Kelvin, make it a useful material for measuring. At oxidation state and trend in chemical reactivity, boron doesn't have +3 oxidation state. It forms only covalent bond. Aluminum is a highly electropositive metal. It loses electron in form +3. Rather than gallium, indium, and thallium, both +1 and +3 oxidation state are observed. As you know, the compound in +1 oxidation state are more ionic than those of in +3 oxidation state. In trivalent state, the number of electrons around the central metal or central atom in a molecule of the compound of this element, example boron, in BF3 will be only 6. Such electron deficient molecule have tendency to accept a lone pair of electron or a pair of electron configuration and thus behave as a Lewis acid. Lewis acid, those who accept lone pair of electron. The tendency to behave as a Lewis acid decreases with increase in size. BCl3 easily accept a lone pair of electron from ammonia. As we know that here BF3, which is a Lewis acid, and NH3, which is a Lewis base. F3b dot NH3. This is an acid base adduct. As you know that AlCl3 achieves stability by forming a dimer. As you know here, see, you can see the diagram also. AlCl bond or the bond length of that AlCl is 206 picometer, while that in a dimer form in middle AlCl form a 221 picometer bond length. Reactivity towards air. Boron is unreactive, or we can say that very less reactive in crystalline form. Aluminium form a very thin oxide layer on the surface which protect the metal from further attack. Amorphous boron and aluminium metal on heating in air form B2O3 and Al2O3, which is alumina respectively, with dinitrogen at high temperature. 2E plus 3O2 gives 2E2O3. As you know the reaction, the nature of these oxides are very acidic in nature. Boron trioxide is acidic. As you know, reactivity towards acid and alkali. Boron do not react with acid and alkali even at moderate temperature. Aluminium dissolve in mineral acid and aqueous alkali, and thus show amphoteric character. What is amphoteric character? Those who can show acidic as well as basic character. Aluminium dissolve in dilute HCl and liberate dihydrogen. As you see the equation, 2Al plus 6HCl gives 2Al3 plus 6Cl negative plus 3H2O. H2, sorry. The concentrated nitric acid renders aluminium passive by forming a protective oxide layer on the surface. Aluminium also react with aqueous alkali and liberate dihydrogen. 2Al plus 2NaOH plus 6H2O gives you 2Na plus AlOH whole में 4 negative aqueous plus 3H2, which is known as sodium tetrahydroxo. We know that we name the coordination chemistry sodium tetrahydroxoaluminate 3. Reactivity towards halogen. This element react with halogen to form trihalide except thallium. Thallium does not form a trihalide. Like we can say that 2E plus 3X2 gives you 2EX3, where X is fluorine, chlorine, bromine, iodine, whatever it is. But thallium does not form trihalides. As you know that AlCl3, it's aluminium trichloride. Okay, boron BCl3, boron trichloride. Important trend and anomalous behavior of boron. The trichloride, bromide and iodide of all these elements being covalent in nature are hydrolyzed in water, and species like tetrahedral MOH whole 4 negative and octahedral MH2 whole 6 3 positive except in boron exist in aqueous medium. The monomeric trihalide being electron deficient. As you know that monomeric trihalide which is electron deficient are strong Lewis acid. Due to the absence of d orbital, the maximum covalency of boron is 4. Most of the other metal halide are dimerized through halogen bridging, which is known as we see in the AlCl3 dimer. The metal species complete its octet by accepting electron from halogen in this halogen bridge molecule. So as you know, to a complete aluminium octet, it accepts electron from chlorine. Some important compound of boron. Borax. It is the most important compound of borax, as we know that it's a white crystalline solid of formula Na2B4O7.10 molecule of H2O. Borax dissolve in water to give an alkaline solution. Na2B4O7 plus 7 molecule of H2O gives you 2NaOH plus 4 molecule of H3BO3, which is orthoboric acid. On heating, borax first loses water molecule and swell up. On further heating, it turns into a transparent liquid which solidify into glass-like material known as borax bead. Na2B4O7.10 molecule of H2. On heating, it gives you Na2B4O7. On further heating, it gives you sodium metaborate, which is NaBO2 plus B2O3. Borax bead test, as you know that. Orthoboric acid. It is a white crystalline solid with soapy touch. Okay, it is strongly soluble in water but highly soluble in hot water. Preparation. How can we prepare orthoboric acid? It can be prepared by acidifying an aqueous solution of borax, which is Na2B4O7 plus 2 molecule of HCl plus 5H2O gives you 2 NaCl plus 4 molecule of orthoboric acid, which is BOH whole thrice. As you see the structure of boric acid here, as you see the BO3 units are joined by hydrogen bond which are in planar. As you see here the pink structure, the red one, the blue one and the green one, these BO3 structures are attached, and all these BO3s or B, the oxygen, the hydrogen bonding is present. They are called the, when a BO3 molecules are bonded with the hydrogen, they are called intramolecular hydrogen bonding and the intermolecular hydrogen bonding. Boric acid is a weak monobasic acid. It is not a protonic acid but act as a Lewis acid by accepting a lone pair of electron from hydroxy ion, for example BOH whole thrice plus 2HOH. There are two hydrogens, 2H positive, gives you BOH whole 4 negative plus H3O positive, which is hydronium ion. On heating, orthoboric acid above 370 Kelvin forms metaboric acid, which is HbO2. On further yield, boric oxide B2O3. Diboron preparation. How it is prepared? Sir, it is prepared by treating boron trifluoride with lithium aluminium hydride in diethyl ether. As we know that lithium aluminium hydride is a very hard or very strong reducing agent. 4BF3 gives you 3Li or plus 3LiLH4 gives you 2 molecule of B2H6 plus 3LiF plus 3AlF3. Lab preparation. How can you prepare? On the basis of 2NaBH4 sodium hydro or sodium borohydride with iodine. Properties. It is a colorless gas, highly toxic, boiling point which is 180 Kelvin, catches fire spontaneously upon exposure to air. It burns in oxygen releasing an enormous amount of energy. B2H6 plus 3O2 gives you B2O3 plus 3 molecule of H2O. Del H is equal to negative 1976 kilojoule per mole. Boron are readily hydrolyzed by water to give boric acid. Diboron undergo cleavage reaction with Lewis base to give boron adduct. As you know that BH3.L. L, what is L? Lewis base. B2H6 plus 2N-ME methyl, Me3 which is trimethyl, 2BH3.N trimethyl gives you B2H6 plus 2 carbon monoxide gives you 2BH3.CO. Reaction with ammonia, it gives you BF3 dot NH3, or we can say that BH3 dot NH3. The structure of diboron, as you know that the formula is diboron is B2H6. The 4 terminal hydrogen atom and the 2 boron atom lie in one plane above and below this plane. As you see in the diagram, there are 2 bridging hydrogen atom. The 4 terminal boron hydrogen atom are regular to center 2 electron bond. The 2 bridge BHP bonds are 3 center 2 electron bonds, which is known as banana bonds, and both the making an angle of 97 degree as one of the end. Boron also form a series of hydridoborates. As you know that the most important one is the tetrahedral BH4 negative ion, which is known as hydridoborates. Both LiBH4 and NaBH4 are used as a reducing agent in organic synthesis. As you know that the 2MH, which is metal hydride, plus B2H6 give you 2M, which is metal plus BH4 negative, which is hydridoborate ion. Uses of boron and its compound. Boron fibers are used in making bulletproof vest and light composite material for aircraft. Boron 10 isotope has highly ability to absorb neutron, or we can say neutron, and therefore metal boride are used in nuclear industry as protective shield and control rod. The main industrial application of borax and boric acid is in the manufacture of heat resistant glasses. Example Pyrex, glass wool and fiber glasses. It is also used flux for soldering materials. Uses of aluminium and its compound. Aluminium is used extensively in industry and everyday life. It forms alloy with copper, manganese, magnesium, silicon, zinc. Aluminium and its alloy can be given shapes of pipe tubes, rod, wires, plates, or foils, and therefore find uses in packing utensils, making construction, aeroplane and transportation industries.